We would like to start, sorry for this unusual appearance. Usually I sit over there and I ask someone else to speak, but today is a very special day. I think it's at the level of a discovery that occurs once in a lifetime, or perhaps in a century. It's really significant for a variety of reasons. Most important of all, it's the detection of a new messenger in astrophysics, and therefore it opens a new window into the universe, meaning that the first signal that we detect is something that we expect. And in fact, theoretical computer simulations were used in order to match the signal. But most important is the fact that there would be many more signals detected, because this was just in the first few weeks of observing. And there might be a lot of sources out there that we don't expect. And that's what happened when we opened the new window in X-ray astronomy or in radio astronomy. I should say that the astronomical community behaved very similarly in every time a new window was opened, because for many years, traditional astronomers were objecting to opening that window. And that was true for X-ray astronomy. There was a committee, an important committee that NASA assembled in the early 60s that decided not to launch a satellite that would look at X-rays in the sky, because there is nothing interesting out there. We know the sun emits X-rays, and so the best we can do is detect X-rays from other stars, and we now know that there is much more out there. The same is true here. We expect compact object mergers, but there could be many other signals out there, and they could reveal new physics. So I think that's extremely exciting. Another aspect of the discovery today is we are talking about gravitational waves as a way of learning about strong field gravity. So it's the first view we have of the space-time near the horizon of black holes. We're talking about a binary black hole system where the two black holes plunge towards each other. So they circle around the common center of mass for many millions of years, but eventually they reach the innermost stable circular orbit and they plunge, because the orbit is unstable, they plunge towards each other. And the burst of gravitational waves that one gets is most of the power in it is coming out in the final plunge. And that probes the space-time near the horizon. So we cannot imagine a better view of the space-time near the horizon than this. So let me just say a few words, because these papers came out, they became available, and there are many of them, and they will all be on AstroPH tonight. And I just had a few minutes to look through them before the lunch. But the signal is shown here on the right, and you can see, I mean, the most important verification of the signal is the fact that it was observed at two separate sites, the Hanford site and the Livingston site, with a delay of a few milliseconds. So just the right delay for a signal moving at the speed of light. The only conceivable other interpretation than this is a real signal would be that some very sophisticated hacker implanted this, someone from North Korea, or implanted it in the data stream, but they really need to know physics in order to do it properly. You can see that the signal, when put together, if you shift by the amount of time necessary, you end up with, within errors, the same signal. And one can see the chirp, the frequency. So when you have two, this is a binary black hole system observed from a distance of roughly 1.3 billion light years. So we're talking about redshift of 0.09 plus or minus 0.03 or so. So about a redshift of 0.1. So relatively nearby universe, but it's a significant distance that we are talking about, hundreds of megaparsecs. And what happens when two black holes, and these are roughly 30 solar mass black holes, we will talk about the significance of that, but when two such black holes in spiral, the frequency of their orbit grows with time, and therefore the frequency of the wave grows with time. That's the standard chirp that you see on the left here. And eventually, they plunge. And you can see also the theoretical model that was used to fit the data as the line that doesn't have noise in it. That's the best fit. So currently, computer simulations were able to, there is a library of possible combinations of masses, spins, and so forth. And they were trying to find the best fit, in principle, for the masses and the spin. And let me give you a sense of what they find in terms of the results. So they actually have a table in one of the papers where they give all the constraints they have on the parameters of the systems. So you can see in this plot here that they just passed, you can see the two masses of the two black holes. One of them is close to 36 solar masses. That's the x-axis, and the y-axis is the second one, which is around 29 solar masses, the central point. And that's plus or minus 3 solar masses or so. They can also tell that the 3 solar masses worth of energy were radiated away in the form of gravitational waves, because they can, it's moving to, because they can measure the mass of the system at the end, the remnant black hole, that shows ring down. So once you form a single black hole, there are still vibrations in the horizon of that black hole that one can detect. And from that, one can infer the frequencies of those vibrations, tell you the mass. And so you compare that mass to the initial mass of the binary, and you find that some mass was lost. This is the mass in gravitational waves. 3 solar masses worth of gravitational wave energy was radiated away. And you can see here the other constraints they can set. They get an upper bound on the spin magnitude of the order of 0.7. Other interesting tidbits, and I'll close with that because that was not a planned presentation for today. They set an upper limit on the graviton mass. So from the fact, if the graviton had a mass, the gravitational wave particle had a mass, then different frequencies would propagate at different speeds because they correspond to different energies. So you have a particle with a mass. Depending on its energy, its speed would change, and so you would distort this wave pattern. From the fact that it matches the theoretical calculation, you can set a limit of the graviton mass being less than 10 to the minus 55 grams, or 10 to the minus 22 electron volts, or if you want, in terms of the Compton wavelength, more than 1/3 of a parsec. Which in a way is not surprising, because if the graviton had such a mass, then gravity would be modified, would become a Yokawa potential on scales of order parsec, and we know that's not the case. But this is a completely independent constraint. The masses of the two black holes are 36 and 29 plus or minus 4 solar masses. The reason this is significant is that you need to start from a progenitor star that was much more massive than that, and the star should not lose mass through winds. So they set an upper limit of about half solar metallicity on the progenitor star, because otherwise the mass loss from winds would be too significant. And the rate of such events is estimated to be somewhere between 2 and 100 events per gigaparsec cubed per year. So that's upward from previous estimates, actually, significantly upward. And it's a wide range because there is only one event that was used for this analysis. I heard indirectly that they might have 2 additional events in the pipeline that are lower significance. Obviously, if you detect an event like that is 28 sigma, the match to the theory is at a level of 28 sigma, then obviously there must be a lot of other events at lower significance. There is an interesting question of how you make such massive black holes and how common they are. There should be a stochastic gravitational wave background, because we detected an event and we can sort of estimate how many such events would take place. per unit volume in the universe, per unit time, and integrate over time. So they estimate, they have a whole paper on that, and they estimate omega, the cosmological parameter in gravitational waves, being 10 to the minus 9, which is very large, because the microwave background is around 10 to the minus 4.5 or so. So this is at a frequency of 25 hertz. The gravitational wave background, the stochastic background, is 10 to the minus 9, very large. They also, there is another paper on a follow-up that was done by IceCube and Antares. These are experiments aiming to detect neutrinos, high-energy neutrinos. They haven't seen anything within 500 seconds of the LIGO event. And they did see 3 neutrinos, but they're all consistent with the background from atmospheric neutrinos. So we don't expect any neutrino or electromagnetic signal. These are silent events as far as conventional astronomers are concerned. There might be one next door and you won't notice it. Well, if it's next door, you would notice it. But in our galaxy, we would not see such events because there are 2 black holes coming together, no matter around them. We expect electromagnetic counterparts when you have a black hole and a neutron star, but these events are completely silent. So detecting them with LIGO allows us a better understanding of the population of black holes in such systems. But moreover, this is a new era in the sense of gravitational wave astronomy. Until now, this experiment was originally funded by NSF Physics. And I actually attended a committee meeting a board meeting where the LIGO people presented their status. And the question arose as to whether they should be funded by NSF Astronomy at some point. And my view was that as long as they build the experiment and perform very challenging tasks in setting this setup, it should be a physics experiment. But as soon as they detect a signal from the sky, it becomes an astronomy observatory. So I think they reached that milestone, and from now on, it will be an astronomer observatory. And there would be, of course, many more events once they operate routinely. But the most important thing for the future is extending the frequency range from tens of hertz, kilohertz, down to lower frequencies, because we expect more massive black holes to produce even stronger signals. In particular, when 2 galaxies come together, supermassive black hole binaries should produce a signal that we can see all the way to the edge of the universe. And we might find many more black holes than we find using electromagnetic radiation in the form of quasars this way. And it will tell us how the supermassive black hole population grew in the universe. So this field, this day is important not so much because of this particular event, but because it opens a whole new era in astronomy using a completely new messenger that was not available to us in the past. Questions? Yeah.
Just strictly speaking, this is an amazing discovery, but when it is framed as a test or confirmation of general relativity, don't we have to be a little bit cautious about that, because the template that fits this was generated from general relativity? In other words, we have no independent measurement of the mass of these 2 objects. So if we knew from independent measurements that these were 2 10 solar mass objects, we would then worry that there's something missing in the strong field of general relativity.
So let me explain it. The situation is very similar to the fingerprint of a person. Okay, there are so many details in the fingerprint. Okay, that if you get a consistent picture with a simple theory, so the nice thing about 2 black holes is black holes are defined by their mass and their spins. It's a finite number of parameters. Unlike a neutron star, which involves matter, where you need to know the equation of state, there are lots of uncertainties. Okay? Here, the system is very simple. It's 2 objects that represent distortions of space-time. So they are fully described by Einstein's equations, no need for matter. The right-hand side of the equations is 0. Okay? And now you solve Einstein's equations with no matter, so just space-time itself, the dynamics of space-time. And you can, of course, change parameters. You can change the masses of the two black holes and the spins, okay? But that's it. You don't have a lot of freedom. And then you get fingerprints. So basically what you get is a library of models of different templates like this. But it's a finite library. So now, there are so many details in this that the frequency is increasing, that towards the end you get these very sharp spikes, that there is a ring down. So that's another completely different regime. You have a single black hole, and now you are shaking it. You have perturbations on it. That has nothing to do with the fact that you had two black holes coming together. This black hole doesn't, it's a new black hole that is now perturbed. And you measure the frequencies of these the oscillations due to the ring down. Each of these, like the initial in spiral, the increase in the frequency, the ring down at the end, each of these are independent, okay? And they're independent elements of the fingerprint. If all of them match what GR predicts for the behavior of space-time, without any matter, so you don't have uncertainties, I don't think there is any, you don't need additional confirmation. It's clear that this is an exquisite test of how GR describes, and by GR here I mean the left-hand side of Einstein's equations when the right-hand side is set to 0. How it describes a dynamical state that is very strongly perturbed in the strong field regime extremely well. Now, we knew it from cosmology. You might say, okay, we knew that GR describes cosmology, but it's a different test because here you have a horizon. The only thing that can be more exciting than that is detecting gravity waves from inflation, because there you have also quantum mechanics in the game. Okay? Here it's just classical general relativity, but in the context of classical general relativity, I don't think there could be something more exciting than this, because you are probing black hole horizon, space-time, and you're probing gravitational waves as a messenger that was not available before. And it's really difficult to get so close to the horizon and probe it, like in the form of a fingerprint. So the other alternative that, of course, is being developed here is the Event Horizon Telescope. And there you get an image, but it's much, in my view, it's less information about what's going on, because you're not measuring the space-time as a time-dependent dynamical quantity as you do here. This is a very transient event. And the more events like that, the better constraints we'll get on alternative theories of gravity in the strong field limit. Moreover, we'll probe interesting astrophysics. Already there are interesting questions. How can you make such massive black holes, from progenitor stars, and how can we match the abundance? Are these relics from the early universe where the metallicities were low? I mean, what exactly is going on? I mean, so when you open a new path, a new window into the universe, there are questions to conventional astronomers that will come up, even though it sounds like it's a physicist experiment. Daniel.
I'm just curious for your opinion, perhaps for Mesh's opinion. There have been lots of lines of argument for the existence of black holes prior to this, of course. And I'm wondering if you would now put this at the top of the list.
Yes.
I would, but
I think if, with a 28 sigma detection, I do think that this is the closest we ever got to a black hole horizon. I mean,
in some ways I find that as provocative as the discovery of gravitation.
I think it's more important. I think that the context of the black hole, and of course you can't probe so close to the horizon better than this thing, this. And so I do think that the black hole component of this story is more significant. Of course, the LIGO community, I mean, they were aiming to detect the messenger, and they're super excited that the messenger was detected. But to me, what's most exciting is what is the message? Okay, so I don't care about the messenger. I think the message that the black holes exist and behave the way we expect them without matter is the big message. It's not, of course, the LIGO team will get a Nobel Prize. I mean, that's clear. If this, holds and there is no hacker in there. And of course, Ray Wise should be commended for his persistence. And in that presentation of Ray Wise that was made a year ago, it was said that he actually predicted the performance and the behavior of the experimental setup 20 years ago, or even more, 30 years, 40 years ago, to be exactly the way it did. And that's a remarkable fit that for such a long stretch of time, he continued to promote this experiment, and he performed as well. Now, the other thing I should say that when I was a postdoc, like most of the audience here, when I was a postdoc, my mentors, the people that were senior faculty at that time, John Bacall and Jerry Ostrecker at Princeton, they said bad things about LIGO. They said, oh, it's a waste of taxpayers' money. We shouldn't really fund it. And that was, I think, a pretty widely shared view of astronomers. You may ask, why is that? And it may be conservatism. It may be that it sounded like it's very challenging. The bottom line is that it was wrong. Okay? It doesn't matter what the motivation or what the arguments were. It's clearly in retrospect, if you look now at what was found and if you think about the future of gravitational wave astronomy, it's wrong. So what is the lesson? The lesson is when people suggest to open new windows into the universe, they should always be encouraged because we never know what we will discover. And of course, here we are excited about the black hole binary system, and that's not, in a way, new physics. We knew that black holes are likely to exist. But what I'm particularly excited about is in the next few years, if they will detect a signal from something that we haven't expected, like a cosmic string, people talked about it, but something even more exotic than a cosmic string, something unusual. And, that will be fantastic. Then, this is just the beginning, in my view. Obviously, if there is something peculiar, some signal that they detected that is peculiar, they would not announce it because they would think maybe it's something in the instrument. They cannot fit a template. They would be very careful about it. But once this field is established, they already have 2 more events, I think, at lower significance. That's what I heard. Once they have many events, they operate for years, they will start fishing for rare fish, things that are not really expected. And I think that will be quite exciting. So altogether, it's an unusual day, and I'm sorry I was so excited I had to stand here and describe it. I'll go back to my seat and ask the speakers of today to say something about other things.
I probably don't need the microphone. Can everyone hear me?
No, but it's recorded.
Oh, I see. All right, forget that.
The internet is watching.
I see.
Just wanted to introduce the speakers today.
Yeah, just wait until introduce.
So the first speaker actually gave the ITC opening today, but we apologize that there was some overlap and some of the people that were supposed to be in the audience were not there because of the announcement from LIGO. It's Jeremiah Murphy from Florida State University, and he will tell us at the lunch about the progenitors of core-collapse supernovae. Then we'll hear from our own Doug Finkbeiner, that will tell us about the first attempt at dust optical properties from optical far infrared in 3 dimensions. After that, we'll hear about another aspect of black holes from the physics department. Prahar Mitra is here. He's a student of Andy Strominger, and he will talk about a recent important breakthrough, or not yet a breakthrough, but an opening for a breakthrough in the context of the information paradox, solving the question of how information, or is information lost when matter falls to make a black hole. And that's entitled Soft Hair on Black Holes. And finally, we'll hear from Jack Singal from the University of Richmond, that is the CFA colloquium speaker today. And he will tell us about the evolution of FSRQ gamma ray luminosity function. Jeremy.
Okay, thank you. So let me just put up the title slide for my talk. By the way, this is the second time in 2 hours that I have to go right after an amazing announcement. I'm starting to think you guys are really trying to sabotage me here. All right, so Josh Jolens and I were really excited about this. We think we have a way to understand the core collapse problem analytically. And if you're interested in that, I will just throw that provocative statement out there, and then you can come talk to me, and then I'll back off a little bit. All right, so most of you know me as a core collapse supernova theorist, but what I want to talk about in these 10 minutes is some interesting work that I and collaborators here have been doing in terms of observations in constraining some of the physics that's going on. In particular, what are the progenitors for core collapse supernovae? This is, do I have a laser pointer? No, that's a pen. There is supernova 1987A. Here's an image taken before it. You see that it was a massive star. So to 0th order, we know that massive stars blow up as core collapse supernovae. This work, Zach Jennings is a fantastic graduate student at Santa Cruz. He started a lot of this work I'm about to show you. It's really cool stuff. Ben and Julianne, JD at UW, I'm partnering with them. They're the ones that collect the massive amounts of data with HST that we're going to constrain with. And Mariangeli and Ben at FSU are graduate students working with me on this. Thank you. Okay. So in my talk that 9/10 of you did not see, I showed this slide of here's a progenitor, cartoon picture of a core collapse supernova. It has an iron core. It's essentially a white dwarf supported by electron degeneracy pressure. It gets to 1.4 solar masses, collapses on a dynamical time scale. But here's the important part that I want to say. I always, in my introduction, say it's somewhere 8 to 400 solar masses. This is a prediction of stellar evolution theory that today we're still starting to get constraints on. And this is the constraint that I want to show you. I'm going to show you the result, and then I'll back off and tell you where it comes from. So this is Mariangeli Diaz-Rodriguez. And this is the minimum mass that we're finding, 7.2 plus or minus 0.2 solar masses. This is a maximum mass we're finding, 33 solar masses. Now, that is kind of interesting given what we just saw today. But be cautious, and you'll see why in a second. Okay, so this is historically how the progenitors of core collapse supernovae are discovered. Just like the image that I showed you earlier, there's a supernova, and you look at a pre-archival images in HST, and you look for the star. A red supergiant, almost always. We haven't seen any other type of star, just a red supergiant. All right. From the various bands, you put together a very rough SED. You put it on a luminosity versus temperature diagram, and you see what initial mass gives you something that looks like that at the end. And this one is, somewhere between 15 and 20 solar masses. The problem with these direct imaging techniques, they're important. Don't get me wrong. We need those. But the problem is that it is rare to get archival imaging. The field of view of Hubble is quite small. There are very few nearby galaxies that have actually been imaged with Hubble. So we only have a handful of these cases. 25 in which we have data for, most of those are non-detections, and 10 are actual detections. So, while I was in as a postdoctoral fellow with various people at UW, Julian came into my office and said, oh my gosh, we have this really cool event that's happening. They, as you know, are trying to characterize the stellar populations in galaxies. And there was this eruptive event that happened in the middle of one of their fields, so they characterized the stellar population. It had a very specific age. From that age, we got a progenitor mass. All right? So this is how it works. We draw a circle that's 50 parsecs around the event. We get the color magnitude of all the stars. Here is the color magnitude diagram. Here is a theoretical model that you put together to try to reproduce this. And from this model, you infer what the star formation history is. So here is the magnitude color diagram. This is the main sequence. This is the red giant branch in these funny observer units. Bright is up here, dim is down there. This is red, blue. So this is the cumulative star formation history as a function of age from now. And what you see is that there is a jump at a very specific age, 10 million years, which corresponds to a very specific mass of the thing that must have died at that time. We do not have the image of the thing that blew up, but we do know, just by characterizing its stellar population, what the mass was. All right? So here is that particular case. Here's the age. And then you find that here's the main sequence turnoff mass versus age. And you can just go to the age, and then you read off the main sequence turnoff mass for this thing. And we did this for several other cases. So just to calibrate this, we did this technique for supernova 1987A. So for those of you that know what the main sequence turnoff is, it's essentially that. except we have all of this data that we're fitting for, not just the main sequence turnoff. All right, and so here is the progenitor mass for supernova 1987A. It's consistent with a lot of things that have been published. Here's another supernova that happened as we were doing this. Even with this ratty data, there's very few stars because this was relatively far away. And I say relatively far away, it was about 8 megaparsecs. We were able to get this star formation history. So there were 2 bursts of star formation. We don't know which one it is. We just say probabilistically it's mostly associated with that one, so we give it an age and a mass associated with that one. All right. So then what we realize is, oh my gosh, we do not need to see a supernova. If a supernova has happened in the past and HST happens to have images, or there are other markers of supernovae, like supernova remnants, we can characterize the stellar populations around those supernova remnants and therefore get the age of the thing that blew up and the progenitor mass. And so that's what we did. So supernova lasts for about 10,000 years. The rate of a supernova in a galaxy is about 1 every 100 years. So any given galaxy, you expect about 100 supernova remnants. So 2 of the nearby galaxies, and you already have 200 progenitors where we had 8 before. All right? So that was what we endeavored to do. Here are the supernova remnants in M31 and M33. This shows the HST archival data that we used. Here's just a couple examples of the stellar population around these supernova remnants. So here's the main sequence. There's the red giant. Here is the cumulative star formation history that we derive. There's a very clear age and inferred progenitor mass. And then here's one that has an older age and a clear progenitor mass. And then sometimes nature is not so kind and we get this kind of mess. It's a combination of there are a range of ages, and also when there's a lot of dust extinction, this is harder to do. All right. Oh, sorry. What you're going to see in a second. Okay, here we go. What you see here is this is after doing this in 2 times, 2012 and then 2014. It's going back. Okay. Oh, come on. There's something about these figures. I apologize for this. There's something about these figures. I think this is correct now. All right. So there's a distribution that you're going to see in a second. Okay. You can actually see the distribution. You can look at it. This is the distribution of progenitor masses that we get. Something we noticed very early on, these dashed lines are what you would expect from saltpeter IMF. And it doesn't matter how you do it. There are far more low mass than high mass than you would expect just from the saltpeter IMF. You know, there's an arbitrary scaling for this curve here. So you either try to make this go up, and there's very few low masses, or vice versa, right? So there's very few. And then I'm going to try to skip this next one because it's just saying that in words. Okay. So initially, Zach Jennings did very nice work in which we tried to compare the cumulative fraction versus mass, that same distribution, and the data are the dashed and the dot dashed lines. Saltpeter, if you just assume a saltpeter would look like that, it is clearly different in a KS test. So even a simple statistic as a KS test shows you that there is something different from the initial mass function, the saltpeter. In other words, everything explodes versus what we're actually observing. All right. So what Mariangeli is doing is we're using Bayesian statistical inference to see if we can't, assuming this kind of model, a minimum mass, a maximum mass, and a power law in between, what distribution do we get? Okay, and here is the answer. Just simple Bayesian inference, we get 7.2, upper mass of 33, and a slope of 2.8 plus or minus 0.5. Okay, so is anyone keeping track of my time?
Yes.
How much time do I have?
Oh, it's just over.
How's that? All right. Let me go to one more slide. So what I want to say is, when we published this result, we were very careful to say either this truly is a maximum mass, or there is a bias against seeing supernova remnants in the youngest regions of galaxies. Right? You would really worry about that bias. And I'll just have to give the punchline. Ben Elwood is looking at this, and we are finding very strongly by just looking at the distribution of, this is the cumulative distribution of sizes of supernova remnants. All right. So I'll go ahead and describe this. This is a cumulative distribution. People have seen this for like 30 years. And from this, people have tried to infer something. For example, they look at this and they go like, oh, that's linear. That must mean all supernovae are in the freely expanding phase, which we know is not right. That can't be right. So what's going on? I looked at that and said, wow, that looks kind of log normal. Ben, once you plot that in the log, and boom, there it is. It's log normal. All right, so what gives you log normal? The set-off phase gives you log normal. You're multiplying 3 independent random variables. Now, it's only 3. It's not, a whole bunch to get you truly the central limit theorem. So we did a quick Monte Carlo simulation to see if we could reproduce it, and we basically do with reasonable parameters. All right? And so the punchline is that to get this, we had to use impossibly narrow density ranges. Impossibly narrow. What do I mean by impossibly narrow? We had to use a mean density for the distribution of densities around supernovae of something like 0.03 particles per cubic centimeter. And this is the width in the log, so it's like a factor. And we're finding a factor of 3. That's ridiculously narrow. That cannot be describing what's actually going on around the environments of these core collapse supernovae. So what we're concluding is that we have to be very careful. Supernova remnants seem to be a highly biased tracer of where core collapse supernovae happened. All right? And so the punchline is, I think this is likely correct because you can basically just see that cutoff at 7.2. But I still worry about this. So I don't know. I mean, does it actually connect? I just thought about this. Does it actually connect? It's kind of interesting that it was 2 30 solar mass things today. There are other reasons people believe that there might be an upper mass around 30. But I just want to give you the observations so far. All right, thank you for your attention.
So is that alpha really inconsistent with saltpeter?
This one is not. I would not say. So you're saying this is, so saltpeter is 2.35.
2.35.
Yeah.
It looks all right.
Yeah, it looks all right. Exactly. It does look all right. The thing is, so for those of you who are just learning Bayesian statistical inference, this is the importance of fitting for all of the parameters at once. When we did the initial paper and we had to either fit for alpha and then, fix alpha and then fit for the maximum mass, or then fix maximum mass and let alpha float, we were getting alphas of 4, right? Or we were getting a maximum mass, or fixing alpha of being 2.35 and getting a maximum mass of around like 30 or so. But when we let them both float, fit for all the parameters at the same time with Bayesian statistical inference, we get these two things that look reasonable. And then there's this tantalizing, interesting thing there that I don't know if it's real or not yet.
So if you look at giant molecular clouds, it takes twiddle 8 million years for an OB association that was formed in a giant molecular cloud to actually migrate away from the molecular cloud so you can actually see it. And it seems that might be a partial explanation for not seeing the most massive.
Absolutely. There are many reasons like that I have in my head that we're trying to figure out. If there are ways for us to use this data to help constrain that, those kinds of things. Because we really need to understand if this is real or not. Well, I want to, as a theorist, try to understand this problem.
All right. It is with some trepidation that I stand up here to talk about something as mundane as interstellar dust. I knew what was going to happen today. The organizers will tell you I tried to get out of speaking today because I did not want to get up here after a talk by my good friend Jeremiah Murphy, but here I am. So I just want to tell you a little bit about what we've been doing with dust and the connection to, believe it or not, submillimeter. So the core of what I'm talking about is this paper by my former student Eddie Schlafly and various people in my group in the Pan-STARRS collaboration looking at the reddening law. So this is just the usual optical to near infrared, how much extinction is there as a function of wavelength, right? And this is using 10 bands of data, GRI, ZY, from Pan-STARRS, and then JHK from 2MASS, and the first 2 bands of Ys. So about 0.5 micron to 5 microns in 10 bands. And what Eddie found here is that you can describe the family of reddening curves you see in different directions on the sky with about 1 parameter. And that's actually a little bit at odds with what other people have found. We can come back to that if you like. But it looks like, to good approximation in the mostly diffuse ISM over most of the sky, you can really just pretend there's 1 parameter. Just don't go too far into the ultraviolet, right? Then it gets more confusing, of course. So the idea here is to use apogee. Apogee is the near-infrared spectrograph on the Sloan Digital Sky Survey Telescope. Use that to measure spectra for about 40,000 stars. And it is a nice pen that we keep up here just to confuse speakers. So from those lines, you can estimate the intrinsic color of the star. Notice that we're only using lines, so the change in continuum due to the dust reddening doesn't affect this. Then compare the measured color to the intrinsic color in 10 bands. Look at that color shift. Then use principal component analysis, the last refuge of scoundrels, to examine the variation and the mean, and then compare this to reddening laws that we already know and love. So just to give a little idea of what these color diagrams look like, here's G minus R, R minus I, out to Z minus Y, and Y minus J. And there are 4 other such plots I could show you. In each case, most of the stars have intrinsic colors that are in the dashed line rectangle here. Right, there is, of course, some color variation. We're using stars over a range of temperatures, not a huge range, but a range of temperatures, and they live about here, and then dust is pushing them in this direction. So this big red arrow in each case is the reddening vector in this color diagram. And the dot colors here are just parameterizing the temperature of the star, because then we can, because different stars end up different places on this diagram, we can go back and ask, do we get the same answer using different stellar, different categories of star? And so this is what we get. The mean reddening law over these 10 bands is this red line. When you do principal component analysis, you subtract the mean and then, find the directions in parameter space that describe the variance the best. So that's why the mean has been subtracted from everything here. So ignore the fact that that's 0. We have to add some constant to all this. But this is the shape of the mean extinction, and then the next component is this blue one. You can barely see on the projector here a bunch of light blue lines behind that. So that's 10 lines for 10 different subsamples of the stars that we used at different temperatures. And that will give extremely similar results. The next component is this green. There's a lot more variation in the green samples you see here. That next component just is not very significant at all. If you want to statistically describe the entire sample of 40,000 stars, it is necessary, but on a star-by-star basis, it's really not measurable. So this is just zooming in a little so you can see that better. Okay, so it's actually really reassuring to get the same answer in 10 different subsamples of the stars that have different intrinsic temperatures. So these plots give some idea. If we go back and compare to reddening laws that we already know about and use CCM is the classic one. A lot of people use Fitzpatrick 99. This is something Fitzpatrick and Massa did just recently where they were more interested in the near infrared. Right, this is going out into JHK, WISE 1, WISE 2. more interested in the near-infrared part of the spectrum, and so then they're parameterizing with something they call alpha instead of the usual R sub v. And then this is the results from our paper using the apogee spectra. This is R prime sub v. We had to give it some other name. It's an RV-like thing, but it's not actually the ratio of AV and EB minus V, so we didn't want to actually call it RV. And so what you see here is the blue line in all of these plots is what we get if we take ratios of G minus R and R minus I shift. So it's basically what is the slope of that vector in that G minus R, R minus I color plot, and then so on for all the band triples here in order. And if you compare to, say, Fitzpatrick and Massa 99 for sort of a mean value of their alpha parameter, like 2.5, it actually agrees extremely well. That's kind of impressive. But the variation about that is actually rather different. If you go back to CCM, it does not agree very well out here. Fitzpatrick 99, which is actually what we used in the recalibration of the Schlegel-Finkbeiner Davis map several years ago. So this is the one that we really leaned on hard and trusted. It's actually pretty good, but again, there are significant deviations. When you have precise data on 40,000 stars, you can really drill down and see these small variations. Now, that's maybe not the most interesting part. The next thing you should wonder is, what is the spatial variation of this on the sky? So this is the whole sky, well, not the whole sky, longitude zeros here, up to about 250. So the sky observed by Sloan apogee. And there's just some dust map in the background. And then the colors are the R prime parameter that Eddie derived. So white is the mean value. When it's low, that's red. When it's high, that's blue. And you see there's a definite pattern here. So apogee observes with these, aluminum plates with fibers stuffed in them that are about this big and cover about 3 degrees on the sky. So that's why you see a bunch of 3-degree patches here. We would love to have such data over the entire sky, but right now we only have it in these pointings. But you can clearly see coherent structures on the sky here. And what this is telling you is Gould's belt dust is different than the dust further away. Okay, can we do this in 3 dimensions? So we've published this 3D rendering map, the Green et al. Map that I've been talking about the last couple of years, and it looks roughly like this. We actually have the new version running right now. It'll be done in about 2 weeks. This is the version from 2 years ago. But just zooming in, you can see there's a lot of structure here. Sorry, these didn't come out very well, but this is 3 different distance slices in some patch of the sky, just to show that they really are disjoint from each other. Here, looking towards Orion, there are some distance slices in another part of the sky. So we have this 3D map of interstellar dust that's derived just from star colors. And what we can actually do is we can let RV, or something like RV, float as a parameter in these fits. And this is especially easy since Schlafly did this as a principal component analysis. You end up with color vectors that are orthogonal in the color space. And because of that, this is much easier to do than if we actually used Fitzpatrick 99 RV or something like that. So my student RV has been working on validating this whole thing with what we call the stellar locus method. So when we're looking at a simple case where all the dust is in one cloud along the line of sight and all the stars are behind it, so there are a few clean cases on the sky you can look at, then you just watch the stellar locus move around in color space and get RV from that. And then we take that and line it up with Greg's code Baystar that is doing this full 3-dimensional Bayesian fit that burns millions of CPU hours. And we can show that we get the same thing. So if this were an hour talk, I could show you lots more interesting plots. But let me just wrap up with this. I said something, I promised you something about submillimeter. This is, I think, the most interesting figure in that Schlafly et al. Paper, even though we kind of just added it as an afterthought. And that is that if we take this R prime sub V thing that Eddie's measuring and compare with Planck beta, So the Planck team parameterizes the dust emission spectrum as frequency to the beta times black body at some temperature. So beta is just the power law index of the emissivity. That ranges from about 1.4 to 1.8, and you see there's clearly an anti-correlation with R prime. Another way of looking at the same thing is, this is a paper I did with Aaron Meisner a couple of years ago. If you treat the dust emission spectrum as being a cold component and a hot component, and you can look at our paper to see why that might be reasonable, and then say the fraction of those two kinds of dust varies from place to place, we can measure that fraction, and we find an equivalently good scatter. So that's actually something new. People have remeasured the Redning law many times, but I don't think I've ever seen a plot. I know I've never seen a plot like this that associates the Redning law in the optical with the submillimeter spectrum of dust. And you can think of lots of reasons, ranging from size distribution to composition variation. You can think of lots of reasons this could be true. And pushing further on this and figuring out what's really going on here, I think, should be interesting. So these are my conclusions.
Here is a question from someone that's worried about both gravitational waves and dust.
Yes, right, yes.
Can you go back one slide?
Absolutely.
Okay. So the scatter plot in the top right there, Planck's determination of beta, I'm not sure how big the pixel size is here or what the signal to noise is on the x-axis.
It's something like 5 arc-minute pixels.
What do you think the signal to noise is intrinsically on the y-axis here? Is this,
Plus or minus 0.1.
okay.
5. Yeah, I think given the scatter in the procedure we're using to get R prime, this is consistent with a perfectly sharp relation, I think. So we really need to measure these things better and see.
Thank you very much, Dan. We need to move on.
Okay.
Hello. Thank you very much for having me today. So I'll be talking about something that's a little bit more theoretical, well, a lot more theoretical than the last two talks. For instance, I will not have a single number or plot in this slides. So I'll be talking about a recent development. By recent, I mean the past 2 years that we've been making with basically Strominger's group over at the physics department here. And in light of those new developments, a recent paper was published by Strominger, Hawking, and Perry, where they took a look back to the original argument of the information paradox and understood it better in light of recent developments. So I'll talk about what the recent developments are and how they modify or help us understand better the information paradox. So let's quickly take a look at what the information paradox is. It's a thought experiment that arises, it's a paradox that arises when I try to apply the principles of quantum mechanics as we understand it today to black holes. So the thought experiment goes as follows. Imagine a black hole of some mass m sitting somewhere here, and I have an observer sitting far off. And there's a bunch of particles which is outside of the black hole, and the observer is all-powerful, and he's able to measure everything that he could measure or that can be measured about the particles. So this is described in quantum mechanics by a state that will correspond to the state for the black hole, and a state which is whatever the state of these particle states are. And this state is going to be a pure state because we know all the information about the particles outside. For instance, this position, momentum, and all of these usual things. So it's a pure state. Then this is the initial state. You let the experiment run. The particles are attracted into the black hole. At this state, you have essentially the same. You have some evolved matter state. The black hole is unchanged because the particles haven't yet entered the black hole. At a next intermediate step, the particles are absorbed by the black hole, and then you have a new larger black hole with a larger mass because of energy conservation. And the state at this state of the experiment is you just have a black hole with some higher mass. However, we know, as Hawking presented to us in 1976, that if I give you a black hole and I ask for what the semi-classical observations would be, you have Hawking radiation. So this black hole will now start emitting some set of Hawking radiation. And the important thing about the Hawking radiation is that it's described by a thermal density matrix, is that it has a certain temperature, and so the corresponding state that corresponds to just the radiation itself is a thermal state, particularly a mixed state. That is to say, the only information you can gather about the thermal radiation is the temperature, and basically all the states in the theory are emitted with equal probability. So there's this, which is the statement that you don't know anything about the state, because if you knew everything about the state, you could tell exactly the probability that it would be for each particular state to be emitted. And then the final state, which is what we'll say, is that suppose the black hole has emitted all of the Hawking radiation that it needs to go back to its original state. So the black hole state is now back to what it was earlier. But the particle state is now a bunch of radiation. We don't have particles anymore. So that's the thought experiment. Now what's the problem with this thought experiment? The problem is the following. I have an initial state, which was a pure state times some black hole state. And then the final state is the same black hole state, and we know it's the same black hole state because of the no-hair theorem. The statement is that the black hole, you only need a finite number of parameters, that's the mass, charge, and the angular momentum, to describe a black hole. And so once you know that those three things are the same, the black hole state has to remain exactly the same. Whereas the matter part of the system has transformed from a pure state to a mixed state. That is to say, we have lost information, or said more precisely, the quantum mechanical evolution of this state is not unitary. And this is a paradox because in quantum mechanics, we always have unitary evolution. So we don't have unitary evolution. So this is basically the statement in one way to state the information paradox as presented by Hawking. Okay. So let's step back and just make sure we understand at least a couple of the assumptions that I'll be questioning today, and I'll challenge them. Firstly is the no-hair theorem. That's the statement that the black holes are entirely described purely by its mass, charge, and angular momentum. That was the assumption. We made that assumption because we said that the initial and the final black hole states are the same, because we measured the mass, for instance. And a second assumption that was somewhat hidden, and it didn't come up exactly, is that the vacuum of quantum gravity is unique. So the observer is sitting far off, and he's measuring particles with respect to a certain vacuum. And with respect to this particular vacuum, he started off with a pure state, and he ended up with a mixed state with respect to the same vacuum. Of course, what might happen, and we know that this happens, for instance, in any kind of curved spacetimes, is that you can have multiple set of vacua depending on what observer you're looking at, and one observer might think that there's no particles, but another observer might think that there's a thermal radiation of particles. So it's important to understand that what you define as mixed and pure state depends on what vacuum you're sitting in. So we've implicitly assumed in this assumption that there's only one vacuum that you could possibly be sitting in. And I'll challenge both of them, and I'll say that in light of the developments that we've made over the past 2 years, that both these assumptions are incorrect. That doesn't solve the information paradox, it questions it. Doesn't mean that we have solved it. So what are the recent developments? So as you probably know, in any system, when you talk about conserved quantities like the energy or the charge or angular momentum or that sort, they're all associated with certain symmetries. And we like to talk about, if for instance in GR, we like to talk about killing symmetries. If I give you a metric, it has some killing symmetries. For instance, for flat spacetime, the killing symmetries of flat spacetimes are translations and rotations, and the corresponding conserved charges for translations is energy conservation or momentum conservation, and the ones for rotation is angular momentum conservation. That's where those charges come from. In GR, this is a slightly more difficult question because the metric itself is fluctuating. It's not a background field. It's not just sitting there, but the metric is changing. So defining killing symmetries in the presence of a fluctuating metric is somewhat more complicated and subtle. What we can do, however, is to define these symmetries at infinity, because An assumption that we often like to make is that the universe is isolated, which is to say all the galaxies and whatnot exist in some finite volume in the universe, and there exists a region in the universe where I can go far away from all of these galaxies and then sit down and make some measurements at that point. So at that point, if I'm far away from every galaxy, to a good approximation, the universe is flat. So then I can ask, and the metric is not fluctuating because there's no matter in that region. So then I can ask, what are the symmetries, what are the killing symmetries of the space-time in that region? So this was done way back in 1962 by Bondi, Metzner, Vandenberg, and Sachs, and they obtained a symmetry group called the BMS group. And as you might, if you were naive, you might expect that because I'm sitting far away, there's no fluctuations, it's essentially flat space-time, so I should reproduce the symmetries of flat space-time, that is translations and rotations. In other words, the only conserved charges, if I'm sitting far away, that I'm allowed to talk about should be mass and angular momentum, which is part of the statement of the Hawking paradox, of the information paradox. However, that's not what they got. It's just a very quick calculation that you can show that you get something called super translations. This super over here has nothing to do with supersymmetry. This was invented before supersymmetry was really talked about. This is just some name that they gave to it. Essentially what it says is that instead of taking a system which has a symmetry of the standard translations in which you take a system and translate everything in the system in some direction, which gives you a symmetry, instead what you can do is, instead of translating everything the same way, you translate angle dependent in an angle dependent way. So you have some given origin and you measure some angle with respect to that origin, and then you can translate each object at a given angle with a different kind of translation itself. What was surprising was that that actually is also a symmetry. That's not an obvious statement, but that's what you just get if I try to work out what the killing symmetries are of asymptotically flat spacetimes, which is what BMS did. So what are the implications of this statement is that this must mean, because there are infinite number of killing symmetries, infinite because it's one for each angle, so it's like a function's worth of symmetries. Because you have an infinite number of killing symmetries, you must have an infinite number of conserved charges. That sounds weird. So the first question is, always you want to ask this, does that actually make sense? Are these symmetries physical? And we understand in modern day that what you might want to call a physical symmetry is something that gives rise to a conservation law. So is there a conservation law corresponding to these symmetries? And the answer is yes. There's a theorem developed by Weinberg also back in 1965. This connection was not established until 2 years ago, but it turns out that Weinberg's soft graviton theorem, which is a certain conservation law of semi-classical S matrices, so that's in the quantum version, it's a quantum version of a conservation law, developed way back in 1965, is nothing more than the symmetry laws, the conservation laws corresponding to these super translations. So this was done. This was in a paper published in February of 2014 by Strominger and his group. So that's one question answered. A second question is, are these charges actually measurable? And the answer is also yes. And this is a memory effect that has been worked out in detail with some formulas by Thorne and Brzezinski also back in 1991. And the effect that they're measuring, the experiment is you set up two gravitational wave detectors, which we can apparently do now, set up gravitational wave detectors, and you measure the gravitational waves go away, and after all the gravitational waves cross, there's a net displacement between the two waves, and it turns out that the net displacement is precisely measuring what this soft charge is. So a quick summary is basically that now we have a good understanding of these asymptotic symmetries. We've set it up over the past 2 years, and we know that they're infinite in number. They give rise to an infinite number of conserved charges. They lead to soft theorems, and by soft here I mean zero energy. And these conserved charges can all be measured. And that's the main takeaway of what we've been doing, which is what I just said. And finally, we can now revisit essentially the original assumptions of Hawking in his paper. Though no-hair theorem is clearly not true anymore, because a black hole, in addition to having mass, charge, and angular momentum, also has these additional infinite number of super translation charges, which can be measured, and in order to give a truly full description of the system, must be measured, and maybe after making the measurement, you end up getting a pure state. And the second statement that we made was that the vacuum of quantum gravity is unique, which is also not true in this statement because I didn't go through it exactly, but soft here means zero energy. So what these charges are doing are basically taking you from one zero energy configuration to a different zero energy configuration. So they're essentially taking you from one vacuum to the other. So even what you were thinking of a definition of a pure state and a mixed state is called into question because you might have two different vacuums to talk about. Anyway, so the takeaway is that we don't know whether the Hawking paradox is resolved, but at least there's a reason to question it. So maybe evolution is unitary. That has to be worked out. So what must still be done, just to be clear, because we get a lot of such questions, the information paradox has not been resolved. All we have done is presented new and concrete tools to address the information paradox in a slightly different way. And certainly what must be done before any claim can be made is, number one, to check that the unitarity is actually exactly preserved. And number two, as we have been recently understood from the ADS-CFT correspondence, is to be able to reproduce the area, the Bekenstein-Hawking law, from a statistical calculation, from a microcanonical ensemble. And so we hope to do that over the next few years. Thank you.
This is very exciting, but of course, what every astronomer knows is that with zero energy, you cannot transmit information. So if these states correspond to zero energy, how can you encode information?
So the information is encoded, for instance, not in the wave itself, but for instance, the memory effect is the following statement. If I give you two detectors, you need at least two detectors for this, and a wave passes by. So the detectors oscillate because the wave changes the distance between them. And that's fine. So none of those measurements are going to measure these soft detectors. However, what was derived by Christodoulou purely in the context of GR, without knowing anything about this, was that after the wave completely passes by, what you may expect is that because the wave has passed by and the system has gone back to its original state, that the detectors are also back to its original state. But the answer that they actually found was that that's not true. If the detector was at some distance originally, after the wave has passed by, the detectors will have now moved to a different distance. And that is the measurement that you would have to make, the difference in the initial and the final distance of the detector that can measure these zero energy modes. So it's not the wave itself, but it's what this after effect.
Yeah.
Yes.
So with the traditional three hairs, we have actually a solution for the metric, right?
Yes.
You can write down the Kerr-Newman metric.
Yes.
So can I write down a metric for a black hole that has got a few extra soft hairs?
Yes. So the traditional no-hair theorem, one thing that is omitted, but it's somewhat implicit, is that a black hole metric is defined the moment you give its mass, charge, and angular momentum up to diffeomorphisms. Of course, I can always change my coordinate and I can define a different metric. However, not all diffeomorphisms lead to identical physical systems. A very trivial example of a diffeomorphism is, for instance, do a boost. Take the Schwarzschild metric and boost it. Of course, that's just a coordinate transformation, but clearly the boosted black hole, which is moving with some speed, has different physical properties compared to the original black hole. So these super translations are essentially exactly those diffeomorphisms that do not die off at infinity, that actually have a physical effect at infinity. And so, yes, basically the answer is that by studying the asymptotic structure of the metric, you can pick out exactly what these hairs are. And yeah, that has been worked out in some detail in the work that we've done.
So they wouldn't satisfy what we would call a stationary solution?
No, like I could boost it, and then I could get a solution that's no longer stationary, but still physically different. That's the same.
Okay, we need to move on.
Okay. Yeah, thank you.
Okay, thanks for sticking around. This is a long title, but I promise it's a short talk. So I'm going to talk about the evolution of the gamma ray luminosity of FSRQs, that's flat spectrum radio quasars, it's a type of blazar. So for context, in the Fermi Gamma Ray Space Telescope, approximately half the blazars that are observed are of this type, FSRQ. What the Fermi data give us in their catalogs is the gamma ray flux and the photon spectral index. With this, plus of course the redshifts, you could determine the luminosities, and then you could get the redshift evolutions of the luminosity and the spectra and other quantities that you like. And we have the redshifts because these nice folks, Shaw et al., have gone out and gotten them for almost all of the FSRQs in the first Fermi catalog, and now the second one even. And I want to mention here another analysis of this same data has been done by the Fermi collaboration, Marco Aiello and others. Here I'm going to discuss the results of trying to do this in a non-parametric way to get it directly from the Fermi and the redshift data. Why is it not straightforward to get it directly? Because the data is highly truncated and biased. If you look at the flux and the spectral index of the data, you get this here, and clearly it's not that those objects aren't there, we're just not picking them up, and that's because of the energy dependence of the point spread function of Fermi. And we're also, just in general, going to miss the low flux, higher redshift objects. Of course, in any astronomical survey that's flux limited, it doesn't mean they're not there. So again, here I want to, taking into account the giant truncation here, I want to get directly the evolutions of the luminosity and the spectral index, and also, given that, we're going to get the integrated output of all of the FSRQs. How am I going to do that? Well, in 10 minutes I can't tell you. So I encourage you to read up if you'd like. We've applied these techniques to various data sets where these truncation effects are there. The 1 penny version is we use a variant of the Kendall-Tau statistical test, but we modify it with so-called associated sets, which form the largest unbiased set for comparison with each object. The results here are presented in this paper. So let's get right to it. The evolutions now of the luminosity, again the gamma ray luminosity, and the spectral index, I'll give them this form here. So a power law. A would be either for the gamma ray luminosity or the index. And this is okay if the objects are pretty low redshift, which all of these FSRQs are. So we're going to look for that power there that describes how these things get brighter as you go back in redshift and how the index changes. And again, applying the techniques that for now remain mysterious, but they're okay. We're going to do a simultaneous determination of the best fit K for both the index and the luminosity. And you can see a surface plot of what that looks like here. Here it is with the 1 and 2 and 3 sigma contours. And so the favored region is right here. So that is a lot of luminosity evolution in gamma rays, big exponent there, and no evolution in the index with redshift. Now the density evolution is how many objects there are in all the redshift bins, and we get the cumulative density evolution with the well-verified Lyndon-Bell method, but again here we can modify it with the associated sets in an appropriate way, and that's equivalent to the maximum likelihood distribution. The derivative gets the differential density evolution, which shows the objects peaking out here at pretty low redshift, which is what we expect. With those, we can form the full luminosity function. So I'm going to have the density evolution there, and what we would call the local luminosity function. That's with the best fit redshift evolution taken out. That is this what we'll call L prime here. So that's the luminosities with the best fit redshift evolution taken out. And again, the luminosity function, the cumulative luminosity function, going from high to low luminosity, we can do the same thing, Lyndon-Bell method, modified with the associated sets. The differential luminosity function is just a derivative of that, and the upshot is this. So here is the local luminosity function at redshift 0, and here it is out to redshift 1, putting in the correct redshift evolution factor, and so on. And this is plotted here with some other results. Now, given the luminosity function and the density evolution, we can then find the integrated contribution from all of these FSRQs at all redshifts and all luminosities and all indexes, all spectral indexes, by integrating over all of them and, of course, putting the flux for a given luminosity in here. And then this would be something we would compare to the extragalactic gamma ray background to see what the contribution of FSRQs is to that. Now, I can... How am I on time? Okay. Well, I'm going to do a little bit. This is, I think math is okay here. So I'm going to do a little bit of integrating by parts. What I want to do is get this in terms of the things that we directly get, which are the cumulative, for example, the cumulative luminosity function. So I'm going to take the luminosity function here and then integrate by parts on luminosity function times luminosity. And we get this here. And so I could be left with one term that integrates over just the luminosity function without the luminosity and the surface term here. Now I'm going to express the luminosity function in terms of oh yeah, sorry, I'm just putting this back in here. Sorry. So now we have the integral with the surface term and this integral, and now I will state this in terms of not the overall cumulative luminosity function, but the local cumulative luminosity function, which is again the direct output. And so again, we're getting the density evolution and the local cumulative luminosity function. So we have this. If we're integrating over all luminosities, then this surface term is 0 because at high luminosities, the cumulative luminosity function is 0, and at low luminosities, the luminosity is 0 if you're integrating over all luminosities. So then we're left with this, and this is all things that we have directly. The local cumulative luminosity function, the index distribution, which I didn't talk about, but we can get it in a similar way, and the density evolution. And the numbers are this. We get that the total output from FSRQs should be this in MeV per square centimeter per second per steradian. And this should be compared with the total gamma ray output of the universe, that's resolved and unresolved objects, which was measured by Fermi to be this. So we get that flat spectrum radio quasars in total give us about 16% of the extragalactic gamma ray background. Here's some other results on that. So that other paper I mentioned to you, I yellowed all 21%. So we're about the same story. So to conclude on that, we've used well-established non-parametric methods, which remain mysterious, to determine these distributions in the gamma ray luminosity and the photon index and the evolutions. They have strong luminosity evolution with redshift. That exponent was big, but no redshift evolution of the spectral index, which is interesting. They have rapid density evolution, peaking redshift 1 or a little lower, and about 16% of the extragalactic gamma ray background. I'm here today and tomorrow, and let me mention this also, that these techniques do work in other bands. So here's some other things that we do with this. The radio luminosity evolution and the radio loudness evolution in quasars. If you form joint radio optical data sets of quasars, they have all kinds of huge truncations here where you're missing objects that are out there. Currently doing this in infrared and X-ray bands, which are more complicated in the truncations because every object has its own limits from these surveys like WISE and Chandra and so on. So I'm here for 2 days. Here's some other things that you can talk to me about that I'm doing. So I mentioned the radio luminosity evolution and radio loudness evolution of quasars, photometric redshifts in machine learning, contamination studies for LSSC optics, and the cosmic radio background, which is the colloquium that we're doing later. And if none of those are interesting, you can talk to me about how the police raided the hotel room next to mine at 4 a.m. last night. All right, thank you.
Take off the microphone.
Right.
It's gone on that long.
Yeah. So.
I don't know what my schedule is like. There's a
Sorry for the time.
Am I on it?
I don't know.
Presumably.